So the first session will begin with a talk by Professor Manaswita Bose. She is a faculty member in the Energy Science and Engineering Department of IIT Bombay, and she is also a co-PI and co-principal investigator of the OpenFOAM project of FOSSI IIT Bombay. So over to you, Manaswita ma'am. You can begin the session. And the talk will be on laminar flow through a pipe. So over to you, ma'am.
Good morning, everyone. You are familiar with laminar flow through a pipe and perhaps also channel. I'll take you through these example problems, highlighting some salient features. Needless to say that you can stop me at any point for discussion. Wherever you have any doubt, just stop me. Okay. Now, the learning objectives are three. One is to connect to the basic form of the conservation laws, to discuss laminar flow through channel and pipe. And the reason I have intentionally taken both problems, channel and pipe, is pictorial representation, schematic representation for both are exactly the same. However, they're different. And I wanted to highlight at this point. I wanted to highlight this point. And then we will discuss a sample problem using a simple wedge mesh. These are the tasks for this session. Now, when it comes to our mind, laminar flow, to be precise, low RE flow. And any idea why I said it is low RE flow to be precise?
Because it is laminar flow, ma'am.
Yes.
So there is a low Reynolds number flow. So we are saying a low RE.
Okay. So what happens if the Reynolds number is infinite? If suppose if an ideal fluid flows through a pipe, will the flow be laminar?
Yes, ma'am. Ideal fluid flow will be laminar.
So that's why these equations are, to be precise, these equations are for low RE flow.
Yes, ma'am.
So when it comes to our mind, the low RE flow, the equations are, these equations are through pipe. The axial velocity is a function of radial position, and that is a representation of fully developed flow. That is, the velocity does not change with axial position. Maximum velocity is given minus dp dz. The minus sign, of course, takes care of the negative pressure gradient. The flow is driven by the pressure gradient, and r squared by 4 mu. Delta P is 32 mu LV by d squared, and delta P can be rewritten in form of a couple of non-dimensional numbers, and where F is the friction factor, which is 64 by RE. This is the set of equations that comes to our mind. Exact schematic representation for a channel flow. However, the equations change. Here X is the cross flow direction. I should have drawn it. X is the cross flow direction. So UZ is the flow Z is the flow direction. UZ as a function of X. U max is 1 minus X squared by H squared. H is the half channel width. U max is given as minus partial P partial Z H squared by 2 mu. Here U max is 3 by 2, that is 1.5, 1.5 U average. So the difference here, it was U average is twice U max. Here U max is twice U average. Here U max is 1.5 times of U average. Delta P is 2 mu L U max by H square. If we write in terms of U average, it is 12 mu L U average by S square. A is the total channel width. H is the half channel width. So there is a difference. And why is this difference? What is this difference due to? The difference is due to the RDR effect. Okay. As we move along the radial direction, the area increases in case of pipe. Because of this RDR effect, though the schematic representation is exactly the same, planar view is exactly the same, equations are different. And that we can see from the Cartesian form of the governing equation and the governing equations in the polar coordinate, and that's the connect I wanted to make. Now, basic form of the equations. First thing, the basic form of equations that we solve is mass and momentum conservation equation, and the assumptions that we make is fluid is a continuum. And I'm sure you would have discussed all these things in yesterday's session, so I will very quickly go past it. Okay. When we say fluid is a continuum, what decides whether fluid is a continuum or not? It is Knudsen number, which is defined as the ratio of the mean free path to the system length scale, and mean free path to the system length scale has to be less than 1. What does it mean? Suppose we consider in the flow domain, we consider a tiny volume. What does this tiny volume mean? The tiny volume, which is a point, refers to an infinitesimal volume. On that point, the average field variables are determined. However, this point contains, this infinitesimal volume contains a large number of molecules. And this is a small exercise I always like to do to give an idea. I do not know whether you have come across this exercise before, but if not, then maybe it's a good idea to take half a minute or so of break to do this exercise. Suppose if you have an imaginary cube of 1 micron a side, okay? Cube of 1 micron a side, and at normal temperature and pressure, which is 273 Kelvin and 1 atmospheric pressure, can you say how many molecules of ideal gas is there in the volume? A quick calculation. We know that 1 mole is contained in 22.4 liter, right? 1 mole occupies 22.4 liter and 1 mole is Avogadro number. Can we do this quick calculation? I don't know, want the accurate number, but just an order of magnitude value. What kind of number we get? Are we doing these calculations?
I think, ma'am, it is 10 to the power 16.
10 to the power 16. 1 micron cube and 22.4 liter. 22.4 liter meaning 1 liter is 1 decimeter cube. Okay, if we do these calculations, we see that this cube contains roughly about 10 to the power 7 molecules, order of magnitude analysis. Now, if a small volume contains these many molecules, so we have enough number of molecules to calculate the average property. So these points represent average properties, averaged over what? Averaged over the molecules, right? And then we get the field variables, which we use in all our macroscopic equations, that is, the field variables, which pressure, temperature, density, velocity, etc., etc. And how else we can see? Suppose when we measure the properties, suppose if we had the sensor probe, which the probe was of the size of the mean free path, then we would see the fluctuations which are seen here. Okay, but if the probe is of the size of larger than the mean free path, these fluctuations wouldn't be seen. So if we are in this region where the molecular fluctuations are not seen, we can say that we are in the continuum regime, and that means Knudsen number is much less than 1. This is the formal definition of continuum. We always say that fluid is a continuum. Okay. Now, when we have established fluid is a continuum, then the other thing we have to do is we have to write down the mass and momentum conservation equation for fluid. Now, mass and momentum conservation equation we have been writing for ages for a system, which is like dm dt of system is 0. This is the total derivative. This is the ordinary derivation. This says that mass cannot be created or destroyed. And this is Newton's second law of motion, where we say that rate of change of momentum is the sum of rate of change of momentum of the system is sum of the forces acting on the system. These two things we know, but we have to write them in terms of the we have to write them for fluid. And when we say if we are writing it for fluid, we write it for the control volume. And this is how, when we write the ordinary derivative for the system on the control volume, this is the conversion. This is the transformation. Okay. The ordinary derivative, there is a partial derivative and there is a flux term. I am not going through the derivation, but I am going to give you the physical interpretation. Again, you may have seen this in the previous lectures. I'll go through it very quickly. The partial derivative term tells you that if we focus at the control volume, and this is Eulerian approach. So if we focus at the control volume, what is happening at the control volume with respect to time alone? That is the definition of the partial derivative. And the flux term tells you that if we focus at the control volume, what is the net influx? What is the net inflow of the property? So, you know, we are talking about the mass and the momentum.
Hello.
Yes.
Ma'am, in the Reynolds transportation theorem, this is the Reynolds transportation theorem, right?
Absolutely.
So what is the system here? Means it is the control volume which is the system, or something else is the system? What is the system in this Reynolds transportation theorem?
No, see, system is a defined mass.
Okay, so how will we define the mass in the control volume?
Just give me 1 second. Can you see my screen now?
Yes.
Okay. So
yes.
I will define the system and control volume. Okay. So system, you see this dark region?
Yes.
Okay. This is system. System is a quantity of mass. Okay. A region in space which you have selected for the study. This is the system. Control volume is something which is a properly selected region in space. So this circle thing you are seeing here?
Yes. Yes.
Where I am using my cursor, this is the control volume. So system is a defined mass. This one is the system which can move, okay, which is flowing, right? You see that this is flowing. So at some point of time, say it was somewhere here, then at time t, it came and occupied the control volume, and then it has left and it is going out. It has partially left, and then at some other time it has completely left and it has gone out. This is the relationship between system and control volume.
So, ma'am, my confusion is in the continuous flow, when there is a continuous flow.
Sorry?
So my confusion is in the continuous flow, can I visualize the system? Means there is a continuous flow. We cannot see
yes,
it
you imagine you are sitting in front of a continuous flow. Okay, some open channel flow or some flow through a pipe where you can see. Okay. Now you imagine you have used a dye and you have dyed a fluid, you have dyed some fluid element. Okay, that you can track. Okay, that becomes your system. Now you are focusing at some point. So that system, that dyed particles, dyed fluid particles come, occupy that your control volume and leaves. You can continuously see. You can visualize it. You know, you sit in front of a river, you see that. Okay.
Okay.
You can check in the lab, you know, if you have a transparent pipe, you can visualize it. Right? And this is precisely what is the depiction of Reynolds transport theorem. That it comes, occupies at some time t is equal to 0, it has occupied at time t plus delta t, it has left. So it has left some volume in between and it has occupied some new volume. And this is that, you know, that dn dt, where n is the generalized property, dn dt of the system when we calculate. This is what is the physical description of the Reynolds transport theorem. Okay.
Okay. Thank you.
Yeah. Now this mass rate of change of masses of the system is 0, and this is what when we write in on the control volume, and here is the momentum conservation. So rate of change of momentum on the rate of change of momentum of the control volume is the sum of the forces acting on the control volume. These are the two equations that we are going to deal with. Rate of change of mass of the control volume is 0. Rate of change of momentum of the control volume is the sum of the forces acting on the control volume. Okay. Now these are the two equations, but this is the integral form. We have to use the differential form. For that, we are making use of the Gauss divergence theorem. And one more thing we have to do, we have to write force in terms of the stress. Okay, surface force we have to write in terms of the stress. This is a second order tensor, which again I think you have gone through in the previous lecture, so I wouldn't go through it in detail. Right now, after we do a little bit of algebra, we get the familiar form of the mass and the momentum conservation equation. We still have kept the shear stress term. Here we will be using the constitutive relationship, which is for the Newtonian fluid, and for incompressible fluid, we will be having that divergence of U is 0. We'll set this to 0. So shear stress is mu into grad U plus grad U transpose. Now, what is incompressible fluid? Incompressible fluid, we define in terms of Mach number, which is the ratio of the velocity of the fluid to the velocity of sound in the same medium. This is important, in the same medium. And if my Mach number is less than 0.3, it is a convention, less than 0.3, we say we will be considering incompressible. That is, change in density with respect to pressure is negligible. Okay, this is the interpretation. With that interpretation, we go ahead, and if we use this, if we substitute this expression for tau, we get this particular equation: rho partial U partial T plus rho U dot grad U is equal to minus grad P plus mu del square U plus rho G. And this is the form of the equation that you know. So for incompressible equation, we have del dot U is 0 and mu del square U. These two equations form the complete set of equation. Of course, because we have this differential equations, nonlinear and second order, we need boundary conditions, and there are different types of boundary condition. You can define the value of the variable itself. That means we can define the value of the velocity itself at the wall. We can define the gradient at the wall. And for heat transfer, of course, this is not for fluid flow. Heat transfer, there is another boundary condition. We'll not discuss that. Now coming to this is the background. Okay, the background of the problem. Now coming to the user point of view, how do we define a problem? Now we will define a problem and we will solve it. Okay, so the problem definition is simulate the velocity profile of an incompressible Newtonian fluid flowing at a steady state through a horizontal pipe with circular cross section. Okay, now if this is the problem statement that is given to you, what are the information that one should know? We should know the pipe diameter, length, properties of the fluid, and velocity and the volume, or the volumetric flow rate of the fluid. Something we should know. Okay, now then properties of the fluid. Okay, now one more thing I should have written here: for analytical solution, if we need to get to any analytical solution, we should make one assumption here that the flow is fully developed. Okay, that's what I have written here. See, when we are writing the boundary conditions here, we said, okay, at the wall, it is no slip condition. That means fluid assumes the velocity of the solid at the wall. And we have written the boundary condition at the inlet and the outlet. Inlet, we have said, for analytical solution, if you want to get an analytical solution, because unless we simplify the equation, we cannot get an analytical solution. So for analytical solution, at the inlet also, we assume that it is fully developed flow. So what does fully developed flow mean? Fully developed flow means, yes.
So velocity profile will not change further, means it will remain same.
Right.
So
absolutely. So that means, suppose if this is the z direction, that means duz dz is going to be 0.
Yes.
Right. So that duz dz is going to be 0 at this boundary is the gradient condition being satisfied, right? We are defining the gradient of the velocity at this phase. And at the other phases, we are saying velocity itself is zero, right? Okay. Now, if we define uniform boundary, uniform flow here, which is for numerical solution, which is possible, we can simulate the developing region. Then this is here for a 2D case, it is going to be a 2D flow here. We can determine the developing length or entry length, okay, which is possible for numerical solution. Now, with this problem statement, we know the governing equation, boundary conditions are set. Now, let us try to get the analytical solution, because, as a first step, when we are learning some numerical technique or some software, in this case, we are not going to get into the numerical methods. We'll straight get into the software. So when we are learning some software, it is better to have some analytical solution at hand so that we can compare the results. So we'll start with the analytical solution. Here I have written the Z component of the momentum conservation equation. I forgot to mention, look at this, momentum conservation equation is a vector equation. So that means it has 3 components. Here we have written only the Z component of the equation because other 2 components are not relevant. You see, it is axisymmetric through a pipe. It is an axisymmetric flow, we can always assume. And R momentum component, there is no flow in the R direction. So the R momentum component doesn't come into picture. So the most relevant component is the Z momentum component. Z component of the momentum. Okay. So assumptions are incompressible Newtonian flow, a fluid given in the problem statement, steady state, axisymmetric pipe flow, laminar we have assumed. So UZ is only non-zero component is UZ, UR, and U theta are 0, fully developed for analytical solution. We have made this assumption. Constant transport properties, that means rho and U are constant and horizontal GZ is 0. We are not considering gravity. Mass conservation trivially satisfied, and Z component of momentum conservation we have written. Now we can see it in both ways. One is because, because of all our assumptions, the left hand side of the equation is 0. That means it is not an accelerating flow. And if the flow is not accelerating, the forces have to balance each other. So there is this pressure force and there is this shear force. So forces have to balance each other, and that is how I think even in any textbook starts. So they write these 2 terms, right? So you can relate to that. And when we write this is then algebra and application of boundary conditions. We get the form of the velocity profile with under all these assumptions. A similar exercise one can do for the channel. And I'm not, see, this is in the Cartesian coordinate system. So the form of the equation changes. However, the principle remains exactly the same, that forces have to balance for a non-accelerating flow. And when the forces balance, we get very similar equation and we solve it. We get a different form. Definitely here, this RDR effect is not there. Okay, so we get set of equations for the channel. Now, flow through channel, OpenFOAM. I think there is a tutorial hands-on session after this, and they will be taking it. I will show you a demonstration for flow through pipe. Okay, so discretization when we take the numerical route, then first we have to discretize the equation. Creation of geometry, creation of mesh, assigning the boundary conditions, selection of properties, selection of solver, setting the convergence criteria, and analysis of results. Okay. Now, see, when we talk about pipe, we said it is axisymmetric geometry, right? If it is axisymmetric geometry, then do we really have to solve a 3D problem? What do you think?
Not necessarily.
When problem is axisymmetry.
Sorry?
We have to solve. When problem is axisymmetry, then we have to solve only one section. Another section will give same result.
Absolutely. So in case, and because it is finite volume method, there has to be a tiny volume we have to solve. So here we can solve a wedge shaped geometry, which is, a delta theta, right? A conical shaped geometry or a wedge shaped geometry. That's what we can solve, right? Now, if you see in the file which you are now familiar with, in a case file, there are some basic directories, right? System, constants, and 0, the initial condition, right? And in system, we have the block mesh dict. In that block mesh dict, we have to define our geometry for the simple thing, right? And there we define the vertices. So here you see we have defined, it's a Cartesian coordinate system. Using the vertices, we have created a geometry like this, which is a wedge-shaped geometry. You know, this is my very poor effort of plotting these points and trying to show you the geometry. See, the first point is 0, 0, 0, and the second point is 0.4995, some number, and 0.02181, and that is how this, then the third point has been created, the fourth point is here, and then fifth and sixth point are there. Like that, the points are created. There are 9 points. Okay. Now, once we do the meshing, this is the simple grading system. So there is the, see, the wall is in the radial direction. So a grading in the mesh is there in the y direction. In theta direction, there is only one mesh, so scaling factor is 1. In the flow direction, we said, okay, let it be uniform mesh. So simple grading with this kind of mesh stretching ratio, and these are the number of grids in each direction. Okay. Once the blocks are created, block mesh is run. Here the boundary conditions: inlet is patch, outlet is patch, and walls are created. There is a wedge. Types of boundaries are assigned, and then we have to run the block mesh. Once we run the block mesh, you know, if it runs successfully, you get this kind of you get to see that, you know, it ends successfully. There is this end comment. Okay. After that, you see, this is the generation of the mesh, and this is the wedge shape mesh, and this is what I meant, that there is a 0.5 stretch ratio. So the smallest size to the largest size is 0.5. And in the other direction, this is the flow direction. Here it is 1. All of them are uniform. And in the theta direction, there is only one cell. So is the geometry clear now? This is the R direction, radial direction. In the radial direction, there is a gradation. There is a expansion ratio. Near the wall, this is the wall. This is the wall. Near the wall, this is the smallest mesh. Okay. Near the center, this is the largest mesh. Smallest mesh to the largest mesh, the stretch ratio is 0.5, and that's what we have defined. If you have seen, we have defined 1.51. This is that 0.5. This is the uniform mesh in the flow direction. In a laminar flow, we really don't expect much to happen. So, you know, gradients to move smoothly rather. So that's why in the uniform, in the flow direction, it is uniform mesh. And in the in the theta direction, there is only one cell. So this is also 1. This is how the mesh looks like, right? After the mesh, we have in the constant directory, we have the transport properties. Transport properties, you see, we have to define only new. Here we have to keep in mind, in OpenFOAM, we define only kinematic viscosity, right? Right? That is mu by rho. Okay. What is the dimension? If we use SI?
Meter square per second.
Okay. Now looking at this number, which is the fluid? I mean, which is the fluid we are using here? Looking at this number, this is water.
Water.
This is water. Okay. So this is the new we have to specify. And after we have specified, we have to give the velocity. We have to define the boundary conditions. Here we have given the boundary conditions. See, this is the uniform. We said, we know numerically we can define uniform bound. velocities also. So in the flow direction, we said it is 0.02500. Other two components are 0. Outlet is 0 gradient. So that means duz dz is or dux dx is 0. Walls are no slip. So this is the boundary conditions we have supplied. Okay. Now start time, end time, and I think down below somewhere convergence is there, which I did not show. You can check this control dict file. Start time, end time, delta t is that. These are the things to play around. Okay, we can change the end time, we can change the delta t so that to check the time convergence and all this. After we run the simulation, we have to go to ParaView, and here comes the analysis. So the I have roughly about 5 minutes time to complete, and in that time I will show you the analysis part. So first thing, we have to plot the velocity as a function of radial position. Now, where do we plot it? See, we know that we started with a uniform. See, this is the length of the pipe section, right? That wedge section. And we know that we started with that uniform inlet condition, and we expect the flow to develop, right? We expected the flow to develop. So where should we plot it? At the inlet condition or closer to the outlet condition, or at different axial location? I would suggest that when we say start the exercise, we plot at different axial position and see how the flow profile changes. It will start from a very uniform profile to a flat profile to a developed parabolic profile. Okay, please do this exercise. I have plotted somewhere close to the exit and it looks like a parabolic profile. Now, how do I know that I am getting a correct result? See, you remember we gave an uniform velocity profile which was 0.025 meter per second, and here look, the maximum velocity I am getting somewhere close to 0.05. So that is twice the average velocity, and that's what one would expect in pipe flow. Okay, and then the other thing we have plotted is the center line velocity. Center line velocity, what I have plotted against center line velocity, I have plotted against the axial distance, right? So you see center line velocity is increasing from 0.025 to 0.05. So now one can check where it is attaining the maximum velocity, that is center line velocity, where it is attaining the maximum velocity, that is 0.05. Look at the graph and check what is the number where it is attaining the maximum velocity. You could get that axial position from the graph, and you can calculate the Reynolds number. See, you know the average velocity, which is 0.025. Now 0.025 is the average velocity. Diameter we know because we have specified the diameter here. Here we can see the half. We can see the radius, which is 0.0005. So 0.005 is the radius, right? So the diameter is 0.01. So 0.01 is the diameter, 0.025 is the average velocity. One can calculate the Reynolds number, and 10 to the power -6 is the nu. So what is the Reynolds number? Anybody calculating? 250 is the Reynolds number, right? Okay, if 250 is the Reynolds number, what is going to be the entry length? For laminar flow, the entry length is L by D is equal to 0.06 LE. One could check these calculations from the, go back to the textbook and check these calculations whether I am getting the correct result. And then the next thing, with the developing length, one can plot the pressure drop. One is in the developing region, pressure is going linear. That means pressure drop is constant. This is one check. The second check is pick up 2 points and put the pressure drop value, put the pressure value. This is calculate the delta P. Calculate the delta P from 32 mu LV by D squared. This is another exercise, and check whether we are getting the values close enough or not. Okay, so this is where one analyzes the result and cross checks. If it is not correct, then goes back and what do they do? Refine the mesh. If it is laminar flow, refine the mesh, and if it is turbulent flow, depending on the problem, they look at the problem setup, problem formulation. And with that, I come to the end of the I think my time is also up. Yeah. Discussion that low RE flow through a pipe and channel is discussed. Implementation of low RE flow through a pipe is on OpenFOAM is discussed, and analysis of results from simulation. How do we analyze the result? That has been discussed. And I acknowledge Mr. Ashley Melvin for creating the wedge-shaped geometry. He was part of FOSSI. And I thank all of you. Okay, if there are questions, we'll just take it.
How can we make wedge-shaped geometry in OpenFOAM?
Okay, so let me go there. See, this is the block mesh dict file. We have to,
Yes, ma'am.
and this is how we have created this is a simple thing. This is how we have created the vertices. Okay, and here we have used the scale factor of 0.01. Okay, you can use any other scale factor, you can use any other numbers, you can play around with this number. I can share this file with you so that you can play around this number. So these are the vertices. This is how we have created the vertices. And then what we have done is then this hex mesh is created, that the vertex are joined to create the surfaces. Number of grids in each block is specified, in each direction is specified, and what kind of grading is required, that is specified here. So once this is done, then the boundaries are assigned. And this is how we created the wedge-shaped mesh in OpenFOAM.
Okay, ma'am. Can you share this file, ma'am?
I will.
Okay. Thank you, ma'am.
Ma'am, I have a small doubt. You said the pipe, we are considering it as a circular pipe. And how is it gonna match the original dimension, ma'am? Like you are considering a wedge shape, and
Yeah.
but the pipe which you are considering is a circular one. So how does it give the accurate resolution for this kind of a mesh, ma'am? I'm not able to.
Okay, so okay. So do you have a piece of paper and a pen with you?
Yes, ma'am.
Okay. So draw a circle.
Yeah. Okay.
Okay. So at any angle. So
Okay,
this is
ma'am.
axisymmetric, right?
Yeah.
So at any angle, draw some delta theta.
Yeah. Okay, ma'am.
So and this pipe, you have this pipe, you have the length and all that remains unaltered, right?
Yes, ma'am.
So if you, instead of doing a full circle 3D pipe, if you just draw this wedge shaped thing, R is not altered, length is not altered.
Okay.
You're just simulating only this delta theta part.
Okay, ma'am. Okay, ma'am. I get it.
Okay.
Thank you.
Ma'am, there is one more question from Siddhi Vinayak. He's asking why you have used expansion ratio in radial direction and not in other direction.
Sorry?
Why you have used expansion ratio in radial direction but not in other direction?
Okay, so see, in radial direction, because there is wall effect in the radial direction. Wall is there in the
Could you
radial.
explain what is the wall effect?
Okay, so see, gradient direction here is the radial direction, right? There is no gradient in the z direction or axial direction. That's why we have used uniform grid in the axial direction and stretch ratio in the wall direction, and finer grid close to the wall.
What is stretch ratio, ma'am?
Stretch ratio. See, can you see this? Can you see my slide? See, this is the radial direction. Okay.
Yeah.
This now see the difference. The size of this grid and the size of this grid. This is different, right?
Yeah.
So this smallest to the largest is that ratio we have used 0.5. That is, I think they call the stretch ratio.
Okay, thank you.
Ma'am, one more question in the chat. Someone is asking to explain boundary condition for velocity and pressure.
Okay. What we have done here is we have used the boundary condition as fixed value. uniform boundary uniform velocity at the inlet, and zero gradient, that is fully developed condition at the outlet. We did not use a pressure condition. Pressure is pressure will get adjusted, and no slip at the wall. That is the boundary conditions we used. You can use a pressure outlet. See, if you don't want to use if you are unsure of its fully developedness and all, you can use a pressure outlet condition, but we did not use a pressure outlet condition there.
Hi, madam. Could you explain once again why we have to use finer mesh in the wall, near to the wall?
See, the gradient direction is the radial direction, right? In this case, flow direction, there is, of course, in the developing region, there is some gradient, but beyond that, we are setting duz, dz to be 0. In the fully developed region, there is no gradient. Now, if you take the derivative, okay, uz ur, what do you get? Minus 2r by r square, right? duz dr is minus 2r by r square. So again, the gradient is 0 at the center and maximum at the wall. So that means the changes in velocity with respect to the position is maximum at the wall, right? So that if you want to pick up, you have to have finer grid there. Okay, that's why we are using finer grid closer to the wall, right? Okay, I'll tell you, I'll give you one small thing. You have a piece of paper with you and pen?
Yeah, yes, ma'am.
Achha. Draw a function. Somewhere it is flat and somewhere it is slightly steep, slightly steeply varying.
Okay.
So where it is flat, you can take a larger gap, right? Within the larger gap, it is piecewise linear.
Yes.
But where it is sharply varying, your gap has to be small. Your delta in the independent variable has to be small. To assume the dependent variable to be linear.
Yeah, the slope will be very high, right? That is what you are meaning.
So that's what I'm saying here, that here the variation of uz with respect to r is large near the wall as compared to it is near the center. So near the wall, it is fine grid as compared to near the center.
And now I understood, madam. Thank you so much.
Yes. Can anyone tell me if there are any other question in the chat?
There is one more question from Rosen. He is asking whether you can use mass flow inlet or mass flow outlet boundary condition.
Mass flow inlet is possible. Mass flow outlet, he can check whether he is getting the fully developed. I need to check before I say. Yeah. For this kind of situation, I always use fully developed. It should develop. It should develop to
a. Madam, just one general question. So,
yeah.
This the finer mesh at the wall, is this will it be this case for almost like all the general flows?
Yeah. Yes.
Yeah, because on almost all example, like whenever like the professors were sharing the screen, like it was observed that near to the wall, the meshes will be always finer.
Yes, that you can this is one thing you can, because you always want to capture the wall effect. Okay, so is there any other question? Is there anything in the chat?
Wall effect means wall shear stress, ma'am?
Wall shear stress in case of, see at the wall, what happens is velocities become 0, right? And then the gradient is high. So that you want to resolve.
Okay, ma'am, Satyanarayan is asking about the boundary condition that you have implemented in axial direction.
Sorry?
Boundary condition that was implemented in axial direction.
Boundary conditions in the axial direction, yes.
Yes, ma'am.
Also at the wall, like no slip at the wall.
Yeah. Also at the wall in radial and axial direction. He's asking,
like every phase we have to give the boundary condition.
Madam, again a follow-up question. So this wall effect, is it something generally people just refer in papers like y plus is equal to something 1 or something
Turbulent
like that?
flow. That is for turbulent flow.
Okay.
I have one minor question here. Sometime at outlet we use pressure gradient, and sometime we use zero pressure. I mean a constant pressure. So, is there any specific conditions where we should be choosing out of these two at the outlet? That when we should use zero pressure gradient, or when we should use constant pressure boundary condition at the outlet?
Zero velocity. You mean zero velocity gradient or constant pressure?
No. At outlet, sometime we use zero pressure gradient, and sometime we use a pressure constant. So, is there any specific criteria of where we should be out of this
pressure gradient? You use zero pressure.
Dou P by dou N equal to 0 at outlet. Sometimes we use like that, isn't it? Or if I'm wrong, please correct me.
Okay, zero pressure gradient is something I need to check. Okay, constant pressure, you can most of in the pressure outlet condition is the most general thing. You don't really have to assume anything. Okay, if you're when you are completely sure that your flow will be fully developed, you can use a zero velocity gradient. Zero pressure gradient is something I'll just check. Unless there is a velocity driven flow, I'm not sure where you are using a zero pressure gradient. I'll just check and I'll take. Okay.
Yeah. No, for example, let's take an example of a flapping wing. So if you are simulating such kind of a flow, you'll have a zero pressure gradient even at the outlet. Sometimes they use that, or sometimes even they use a convection boundary condition. Sorry, ma'am.
It's problem dependent. I'll have a look at the problem. If I look at the problem, I'll be able to tell you.
Yeah.
So boundary conditions are essentially problem dependent.
Yeah. So I was just wondering that is there any criterion where we can choose out of these two? That okay, this time we'll go through pressure constant, or maybe next time I can go through zero pressure gradient, something like this. So is there any some kind of criteria?
We have to look at the problem.
Okay. Yeah. Thank you. Yeah. Thank you, Prof.
Ma'am, one more question. So when you're simulating this flow of through a pipe at the inlet, generally we prescribe the velocity and the pressure is prescribed as del P is equal to 0, and outlet we say the del of U is equal to 0 and P is equal to some P outlet. So is there any reason why it is like that generally? I mean, why we don't prescribe the pressure at the inlet instead of the...
See, if you define the pressure at the typically in general, what happens is when we simulate something, we simulate the practical problem, right? And we know in any experiment you can think of, we know the flow rate. And that's why we define the flow rate at the inlet, either the mass flow rate or the uniform average velocity or something, right? That's what we define. And at the outlet, what happens is we do not know the exact velocity profile, right? So sometimes somebody
madam, this is with respect to the pressure actually. So
I'll
generally
I'll tell you. So at outlet, we typically do not know the exact velocity profile. So somebody mentioned that can we use a mass flow outlet mass flow condition? That is one way. Sometimes, and most of the times, we know the pressure. So we can give a pressure outlet condition. If we give the pressure outlet condition, and a velocity inlet condition or mass inlet condition, pressure at the inlet gets adjusted. We don't have to define the inlet pressure again. Okay, so only if a pressure driven flow, we don't have to define the inlet pressure again, it gets adjusted. That's why we don't define the pressure inlet. If we define inlet pressure, we don't have to define the inlet velocity.
Yeah, that is my confusion, madam. Like you told that the pressure gets adjusted. Like I did not understand that particular point. If you could explain that.
Okay. I'll show it to you from the laminar flow, right? Using laminar flow, that is easy. So see this equation. See, pressure gradient is related to Umax, and Umax is, of course, it's the Umax is related to the velocity profile is related to Umax is here. So pressure and pressure gradient and the velocity profiles are related to each other, right? So now, if we know the inlet velocity profile and the outlet pressure, the inlet pressure gets calculated. If we look at this, so UZR is what? Minus partial P partial Z R square by 4 mu 1 minus R square by small r square by capital R square, right? Okay, and this, if we say that, and this is linear, say in case of fully developed flow, I'm just saying this is linear. So I'll write it delta P by L. So delta P is P inlet minus P outlet. So if I know P outlet and if I know inlet velocity profile, inlet velocity, P inlet gets calculated, and that's what I. Okay.
Oh, okay, ma'am.
So we don't have to give the inlet. See, flow will happen because of the pressure gradient. Flow we know, outlet pressure we know, inlet pressure gets calculated. Right?
Hello, ma'am.
Hello.
Will we get any error if we prescribe the pressure at the inlet, like interchange, like we instead of prescribing the pressure at the outlet, along with U inlet, if we, I mean, this is general, not with respect to this example I am asking, but generally if you look at.
In general, I think so outlet you have to give a boundary condition, right?
Yes. Yeah. So generally, it is mentioned that at the inlet you prescribe the velocity, and at the outlet you prescribe the pressure.
That is the most general boundary condition.
Yeah. So I was trying to figure out the answer for that. Like, why is it so? Like, instead, can we also? Why can't we prescribe the pressure also at the inlet, like velocity?
So if you see. No, if you define pressure inlet and velocity outlet.
Yeah, like have the same boundary condition for the you have the U inlet and delta U is equal to 0 at outlet. Same thing for pressure also, like P inlet and delta P is equal to 0.
I think that will be over specified. You can try. I mean, I do not know, but I think one of the boundary conditions or something will be overridden. That will be there within the code. You can try that. Just try and see what happens.
Okay. Okay.
See if you define both pressure and velocity at both inlet and outlet, I think it is. I mean, it is going to be over specification.
Yeah, what I was meaning was at the inlet you say P is equal to the inlet pressure, and outlet you specify the gradient delta P is equal to 0.
Delta P is equal to 0. You can say delta P between what? Like the partial P partial Z is equal to 0.
Just saying 0 gradient at the outlet. Generally, it is the other way around. We pressure.
I don't know. I actually see you cannot have the Z. See, if it is a pressure-driven flow, you cannot have the. I can't see how you can have a Z. I can't see how you can have a Z delta P delta Z 0. Okay, there has to be a pressure gradient, right, for the flow to happen, no? If it is a pressure driven flow, there has to be a positive pressure gradient for the flow to happen, right? I mean, negative pressure gradient, positive delta P for the pressure to happen, for the flow to happen, right? So I do not see for a pressure driven flow how you will set the delta P delta Z 0, but what you could try to simulate, you could try and see what happens in different solvers, defining pressure inlet and pressure outlet condition, and see how the flow develops.
Okay, ma'am. Yeah, that I will try.
For example, suppose if you have already a developed flow, you know the U inlet, U outlet, and all these things, you know the pressure at inlet, give that same pressure conditions and see how the flow develops. That should develop. Just check that. You can check that. Run a simulation.
Yeah.
Okay.
Yeah, sure, madam. Thank you so much.
For a pressure-driven flow, I don't see how we can give the delta P delta Z 0 at the outlet. That I don't think it should work.
Hello, ma'am. Thank you. Good morning. and thank you for your lecture. Ma'am, I am having one doubt. Like already I was, I have seen in the Fluent that they for boundary condition they have mentioned that if we are simulating a like constant density flow, incompressible flow, then in that case velocity inlet and pressure outlet is the most convenient boundary
That's the
condition.
most common.
Yeah, but for for compressible flow, they prefer mass flow rate inlet at inlet boundary condition and at outlet mass flow rate outlet boundary condition. So here I'm getting confusion. So from the basic conservation principle, whatever the flow, it's maybe a incompressible, compressible, or a developing or fully developed flow. This mass flow rate must be conserved at both of the inlet and outlet. Then why cannot be used? And I have tried this mass flow rate inlet and mass flow rate outlet as a boundary condition for incompressible flow, and I was getting a solution which is having a kind of deviation. I was not getting a correct solution. So I'm having this doubt.
So that is very specific. Like no, that is a very specific numerical question. We need to check that. We need to check which algorithm you are using and all.
Ma'am, like whatever algorithm we are using, but
your question is valid. It should work. We need to check that.
Okay. Yeah. Okay, ma'am. Thank you.
Yeah. Okay. So I think we can end this session, Professor Manaswita.
Yeah, I think so.
Yeah. Okay. Thank you so much.
Yeah.
It was such a wonderful session. So many queries and very much informative. Thanks a lot.